Welcome back to another Ramda JS video, and this video is probably going to be a very short video because we are going to talk about the functions dec and inc, which essentially are short for decrement and increment, so decrease by 1 and increase by 1. So I mean, what am I gonna say? Dec decreases by 1 and inc increases by 1, right? But I mean, let's instead just try to define these functions and maybe jump into not the documentation, but jump into the actual source code and see how they defined it. But I mean, if we just look at it here, so dec is a unary function that takes a number and produces a number. And I mean, as the description says, it decrements its argument. And then they say, see also inc, which, so now we're jumping forward in the documentation because these are essentially sort of the inverses. Yeah, maybe they're the inverses, where the only difference here is that we say increments its argument, right? So, I mean, you decrement and you increment, but let's jump back to dec. And you can see here in the example where they do R.dec 42, and that yields 41, right? And I mean, recently we learned that you can actually also press expand, or I mean, sorry, recently I realized that you could actually press this button. Probably you already knew this. I'm sorry. But then you can also see that the argument here is, they name the argument n, and then they say that the function returns the number n, so n is a number, minus 1, right? So that's decrementation. So I mean, let's jump into Node here, and let's say const r equals require Ramda, so that we have Ramda. And then let's just say R.dec of 10, that gives you 9, right? R.dec of 11, that gives you 10. So, I mean, that's not necessarily very interesting. I mean, again, like, except that, of course, you can, as we've talked about, like, you can use these in pipelines, again, like, to construct point-free functions, so for pipe or compose or something like that. So, like, you could say, actually, let me use let so I can reuse the same variable. So, let's say you have a function which pipes through R.dec and then R.dec and then R.dec, right? Then you've essentially created a function that subtracts 3. So if you then pass 10, you get 7 because you're running 10 through decrementation, and then you're running that result through decrement, and then you're running that result through decrement. So that gives you 7. So I mean, that's cool. That's the way you could use decrement. But of course, I mean, let's think about these functions. Like, if we would define these functions, how would we define them? I mean, it's very simple, right? Like, let's say we had a function, let dec, and it takes some x. Actually, let's maybe say some n. Actually, let's say some x. Takes some x, and I mean, it just does x minus 1. That's dec, right? Like, dec 10 gives you 9, dec 11 gives you 10, and then you can do the same thing, the same shenanigans here. Like, let, sorry, that's not what I wanted to do. You can do let f equals, and instead of R.pipe, R.dec, and so forth, let's just do dec, because that's the one we define now. Dec, dec, and dec. And that, oh, sorry, of course, because f has already been defined, so I have to reuse the same variable. I'm just changing the contents of f. Shadowing? Anyone? Anyways, no, whatever. So f equals this new function, and so then we can run f again on, let's say, 10, and then we get 7. So that seems to work as well. Like, we run it on 11 and we get 8. So even with our own defined decrement function. But I mean, that's one way of defining dec, right? Like, dec is a function that takes some x and returns x minus 1. And of course, I mean, that's the most efficient way of defining it, probably. But I mean, another way of defining it is in terms of add. Sorry, in terms of subtract. Another way of defining inc would be in terms of subtract. Oof. Another way of defining inc would be in terms of add, and another way of defining dec, so decrement, would be in terms of subtract. So we could also say that the decrementation, can you even say decrementation? Can somebody please let me know in the comments? Anyways, side note. I mean, another way of defining dec is to define it without a point, quotation marks, like a point-free version of dec would be to say that it's subtraction where you don't know the first argument, but you do know the second one, and that's 1, right? So we talked in I think the last video, we talked about currying. So then you should know the r.__ syntax. And if you're not familiar with that, check out the last video. So that should also work. If we then dec 10, we get 9, right? Because it's the same thing as saying subtract 10 and 9. Sorry, 1. Subtract 1 from 10. But then we're saying, well, we don't know this argument, so I'll put __ here, and then we'll say that's the definition of dec. The definition of dec is to subtract 1 from whatever number you have. But and then, of course, I mean, we could also just say R.flip R.flip. R.flip, R.subtract. So we're flipping the arguments of subtract, and then we're passing 1, right? That's another sensible or valid definition, or valid way of defining implementing dec. So then we pass 10 and that works, we pass 11 and that works, we pass 12 and so forth. I mean, that works, right? We just flip the arguments of subtract. So I don't know, like, how would we make this interesting? I guess, like, let's just say we could just maybe this. I mean, so probably this makes perfect sense to you, but just to sort of hammer this in, what I want to say is that if you've been following along in the series, hopefully you're also feeling that we're learning tons about functional programming. Like I've said in the comments numerous times that I know way more about functional programming now than what I knew when I started doing this video series. But also, hopefully you're feeling that some of these functions are becoming extremely trivial to implement yourself, because you're realizing actually there's not a lot of magic here. There's just a bit of, I mean, the composition is essentially the magic. And hopefully you're seeing how it's pretty darn awesome to use composition, because you can just build all these very complex functions, obviously not as dec, right? But you can build these very complex functions by using these very small pieces, and these same old pieces just show up time and time again. So, I mean, let's think about it this way. What if we want to define dec as the subtraction of, actually, again, let's use that, the flipping of subtract, so let's call that sub, and then we pass 1 to that. The flipped version of subtract, where we partially apply it to 1. So notice here that I'm not using R.subtract and I'm not using R.flip, so let's define these ourselves, right? So maybe I should actually, sorry, because I'll just forget that, so let's just say flip sub 1, okay, because that doesn't work because we don't have flip, but now we have that in the history of this, well, scrolling upwards here. So then let's define flip, right? So flip would be something like, well, it takes a function as an argument, and then you want to flip the order of the arguments. That means we first take an x and then we take a y, and if we didn't flip the arguments, then we would apply first and then we would apply, then we would apply f to x first and then to y, but actually since we're flipping, then we're first applying it to y and then to x, right? So notice how this is the first argument and this is the second argument, but we're flipping it, so now we're first applying it to y and then we're applying it to x. And notice here also that I'm explicitly constructing a, let's say, curried function, right? A function that is partially applicable. So we're not using autocurrying, which means we don't get the benefits of, let me put it this way, if we define that, I can't call flip f x y. That doesn't work. Then it's only going to run f. I have to call it like this, f x y. So you have to use some method of autocurrying in order to support that alternative syntax, so that this essentially becomes syntactic sugar for this. Sorry, now my God, flip. It becomes syntactic sugar for this, right? That you have to use some kind of autocurrying, which, I mean, you could define autocurry even yourself, and maybe actually I should do that. So if I remember, I'm definitely going to do that in one of the videos. We should have done that in the we should have done that in the curry video, but yeah, some other happy time. But anyways, if we don't worry about this sugared syntax and let's just use this explicit partial application, or let's assume that all functions are taking one argument at a time. Then we've defined flip, and what we need to define is sub. So sub would then take 1x and then 1y, and then just sub or subtract y from x, right? So sub 10, 20 means -10, right? Because we're subtracting 20 from 10. And this is why when we partially apply it and we say sub 1 and assume that that's going to work like decrementing, it doesn't, because if we say dec equals sub 1, that doesn't work, because if we then say dec 10, we get -9, right? Or let's say maybe this is more obvious. Dec 0, we get... Wait, what? It wasn't more obvious. We take 0 and subtract 1. I'm so confused. I assumed that we would get -1. I mean, because 0... What? Sub is defined... Let me just look. I mean, sub is defined as x. You take x, you take a y, and then you subtract y from x. So if we apply it to... Yeah. Why am I being so stupid? Sorry. Sorry, okay. So if we've now defined dec as a function that that subtracts whatever number we give it from the value which it is already partially applied with, which is 1. So this should maybe be called something like difference between 1 and this number, right? Or so let's say let's call it distance from 1, right? That would be maybe a sensible way of naming this function dec1. No, sorry, not dec1, sub1. Like this, right? Because then we would say distance from 1, and if we pass 1, then that's 0 because they're the same number. But if we pass -1, that's 2 because the distance is down to 0 and then down to -1. I mean, something like that. We're just making stuff up right now, right? But I mean, that would be one way of thinking about it. But okay, so enough of that. This is the wrong definition of dec, for example, because, or I mean, the wrong definition. It's an unintuitive definition of dec to just say this, because that's probably not what we mean when we say decrement. What we mean is probably the flipped version, right? So now we did define flip, right? So we've defined flip, so we can say that dec is the flipping of subtract, so sub, and then partially applied to 1, right? So then we can say dec 10, yeah? And then we get 9, right? We dec 9, and then we get 8, right? So dec 10, we get 7, right? And then we can use R.pipe. We'll use our own decrement function. Let's use it 3 times, and then let's call that. Let's pass 10 to that function that we've constructed, and then we have 7, right? 11, then we have 8. So, I mean, you can see this works fine, and hopefully, if you feel comfortable with this, you're hopefully also feeling that you're becoming really comfortable with composition, and probably you're feeling then that we can even get around or get by without using libraries such as Ramda. It's not obvious to me that we always need to use them. So, for example, in the series where I built where I did game development, or where I'm doing game development using JavaScript and sort of using functional programming style, or I'm writing games using JavaScript in functional programming style. And there, I'm not actually using any libraries, and I'm not actually suffering very much from it, because most of these functions are actually, most of them are trivial to implement yourself, right? And some of them are well known, or maybe I shouldn't say some of them, all of them are well known. So if you're too lazy to think about a particular implementation, or feel like it would be a waste of time to think about it, such as, for example, transpose, right? I'm currently working on a video for that series where we'll talk about Tetris, where I'm implementing Tetris, and then we use transpose, and transpose is one of these well-known functions. I think transpose is probably in here in Ramda. Let's check. I mean, if we just search in the filter here, yeah, I mean, transpose is in this list of functions here, so it's well known. So you can just copy the implementation from somebody else, and I don't necessarily think we have to. I mean, this is not algorithms class, so you don't have to worry about that, right? Whenever you have the time, you can study that function and learn what that function does. But since it's so well defined, and since it's so it's obvious what output we get when supplying some particular input, it's not a huge problem to copy that code, right? I mean, it's a huge problem to copy code when you don't understand every nuance of the relationship between input and output, or if you have if you're copying code that mutates, that's a completely different thing, right? But in functional programming, most things are so well boxed, right, that it's not necessarily an issue. Anyways, what I'm trying to say is that then we can just redefine basic functions such as map and so forth, so that they are following this syntax that we talked about here, right? Like where you have to call sub like this, and not like this, because you don't have auto-currying. And then you have zero overhead because you don't have to worry about getting Ramda in. And I don't mean overhead as in like performance, because probably Ramda is more efficient than if I would write the functions from scratch. But then I have less to think about because I can just start up node, get coding, and I'm just like hacking away, and super quickly we're moving towards things that are making sense, and we're being productive. Okay, so now I'm totally on a rant, and this is completely irrelevant for Ramda. Was there anything more I wanted to say? We redefined flip. We redefined sub, and then through that we then built dec. Let's actually, before we do that, let's jump into the source code and let's just check out the way they defined it. I mean, I would guess that they defined it just strictly using subtracting 1 for performance issues. Like, it doesn't make any sense to use composition, but we just used composition just because it's interesting to, again, like, to practice our capacity to use composition. But yeah, actually, I mean, you can see here they actually did define decrement in terms of adding. Oh, okay, not actually in terms of subtracting. They defined it in terms of adding -1. I have no idea whether there's maybe some performance benefit of doing that rather than by using subtract, but who knows. Okay, actually, sorry, maybe they defined subtract in terms of flipping the number, like adding a negative sign, because then that would make sense, because then there would be another function call if they would define it like if they would define decrement in terms of subtract, and if subtract was defined in terms of add, then there would be an unnecessary hop, and then it's just faster if they would define it in terms of add. Let's actually, I mean, let's super quickly jump back source here, and let's go to not add but subtract, right? So PRS subtract, and let's just see, did they define that? No, they didn't actually. They did this. So yeah, I don't know. I mean, if you have any idea about why they did this, why they defined decrement in terms of adding -1, ooh, no, of course, sorry, of course. That's interesting. That's interesting, because the order of the arguments don't matter, right? So in subtraction, the order of the arguments matter, and this is why we had to do as we did now. Either we have to do a flipping of subtract and then pass 1 in order to have a function that when we invoke it with a number, we decrement that number by 1, right? So this is the function part, right? To the left of this final number. I'm just not saving it into a function just to save time, right? So this is the function part. This is what I would put in a variable called f, or actually I would call it dec. But then we have to flip this subtract function, or we have to do r.subtract and then partially use this sort of wildcard notation, I guess you could call it, and then so partially apply the second argument, like partially partially apply the function such that we begin by applying the second argument. Probably my language is incorrect here, but whatever. With 1, and then we pass this underscore as the first argument in order to say that that's the number, that's the argument I don't know yet, and I want to leave that for partial application later. I want to have a function that expects that argument back. That's another way of creating this subtracting function, but these probably cause more overhead, because then you have this, yeah, probably, definitely, because then this would probably define a new function when you do this subtracting, because here you actually, both of them would, no, both of them, yeah, I don't know. I mean, let's not dig into the details. Presumably, both of them would have more overhead. Presumably, both of them would be more expensive, because here we're partially applying, like this is like the R__ thing is probably more complex than just doing normal partial application in the sort of order that the arguments appear. And but when they then do add, I mean, it doesn't matter if you add 10 to 100 or if you add 100 to 10. I mean, you're going to end up with the same number. So if you then add -1 to, I mean, yeah, if you then add a -1, that means you're subtracting 1 from whatever argument you're passing later. So yeah, that's of course actually, that's pretty elegant. That was a smart way of doing it. Now that's cool. Now I realize. Yeah, and let's think about that. I mean, even if our add was the other way, like even if we had the flipped version of add, we could still say we partially apply it to -1, right? We get a function back, and then if we call that function with 300, we're still going to get 299, right? Because we're adding the number -1 to whatever we had before, which always is decrement. Yeah. These are the moments when it's obvious that I haven't studied math enough, right? I'm like, oh my god, revelation, that is pretty cool, but actually it's like fairly obvious. Anyways, let's cut here. kudos to you if you stuck around in this video this long enough, and hopefully you found this discussion interesting as well. Thank you very much for watching. I will see you in the next Ramda video. Don't forget to subscribe so that you won't miss the upcoming Ramda videos. And yeah, thanks for watching. I'll see you in the next one. Cheerios.